So good evening everyone, I am Shivani Dhok and I'll be taking your tutorials on the course of digital signal processing and its application every week on Friday 6 to 8 p.m. and you people can stop me at any point and ask your doubts by unmuting yourself. I'll request you to unmute yourself and ask the doubts instead of typing in chat box. Also, you people can raise hand before asking doubts if you want, or you can just simply unmute yourself and ask. So every week I'll take the tutorial based on the content that is covered in that particular week. So I shall be discussing very briefly or basically having a recap of whatever content was covered in that particular week, and followed by some questions which are related to the content of that particular week. So these questions may belong to the assignments that were there in previous years, or else from some other books or some other questions which are created by me. Anything I can take in this. The main aim of these questions will be uh, making you understand the concepts in a better way. So let's start with today's tutorial with recap of week 1 content. So this week 1 was a lot like a recap, uh, or rather an introduction kind of thing, where some basic terminologies were introduced, which include continuum, discrete, sampling, sinusoids, sampling of sinusoids, aliasing, discrete system, etc. So the very first concept that was introduced was this continuum. And what does this continuum say? That if I am having two values, let's say 1 and 1.1, so I can find whatever value you give me between these two will be present here, will be present on this line, which indicates this continuum thing. But when we are having a discrete thing, if I have 1, 1.1, 1.2 and so on, like that is a sample or a step size of 0.1, then I can't find 1.05 between these two values. So that is discrete. And the way we go from this continuum to discrete thing is by sampling. So this continuum to discrete with respect to the independent variable. So basically when we are having a signal, any signal, let's say xt, can be represented or is basically a function of an independent variable, let's say this t, which leads to a dependent variable which is xt. So any signal is a function that maps from a dependent variable to an independent variable. So when we are doing this sampling, we are making this continuous independent variable to a discrete variable. So that process is done through sampling. Next thing that was introduced was the sinusoids. So the sinusoids are very special kind of signals which are continuous, which are smooth signals, which have derivatives. Any number of time you can take its differentiation. You can differentiate it any number of times, and it is analytic. Like yeah, it's a very special kind of signal. And these sinusoids can be used to represent other signals which may have discontinuities as well through Fourier transforms and other tools. So yeah, these sinusoids are interesting. Then the concept of sampling of sinusoids was discussed, like how to sample a signal which is xt, equal to cos 2 pi ft, or let's say fct or f naught t. And in order to sample this, what we do is we take the sample at every nth instant of sampling duration. This ts is sampling duration, and this we call as x of n. So this is how we get the samples of sinusoids, or rather this is the way we get the sample of any continuous time or continuous independent variable signals. Now the concept of aliasing was introduced. So what it says is, when we are doing this, then along with this particular frequency, some more sinusoids also generate the same sample value. Like multiple sinusoids generate the same sample value. So when we want to reconstruct it back, reconstruct the discrete, the continuous time signal from its discrete samples. So in order to uniquely reconstruct it back, we need to satisfy the condition that the sampling frequency Fs should be greater than 2 times the maximum frequency present in that particular signal. If this is not formed, then we'll have overlapping of samples or overlapping of signals or sinusoids which contribute to that particular sample value which we are having, and that overlapping thing is known as aliasing. After that, a brief introduction for discrete systems was given. So what does a discrete system say? We are having a discrete input, independent variable. The dependent variable, this xn, is still a continuous, still has continuum. It passes through some system and gives a discrete output yn. So this system then is discrete. And in next week we'll see the characterization of this LSI systems and other things. So this was all that was covered in week 1. If you have any questions, then let me know. Otherwise, we'll start solving some sample questions.
Please explain once more the aliasing. Please explain it once again.
Aliasing thing. Okay.
Yes.
Yeah, fine. Let me add a page there. Okay. So let's say I have this signal xt equal to cos 2 pi f naught t. So if we take its frequency domain representation, then what it says is we are having this cos, or let's say we have some phi also. This was done in class. So we have, this is f naught frequency, this is frequency. So here I'll have a signal of amplitude a and phase phi, and when we are sampling it, at sampling frequency of fs, let's say this is fs, this is 2 fs, then we will be having uh, a component present at f naught, fs minus f naught, and fs plus f naught. Similarly here f2 fs minus f naught and 2 fs plus f naught, like that we'll be having these components. So how it is happening is, so this cos thing looks something like this. Let's say this is the original frequency, original cosine wave, and let's say I sample it like this, here, here, and so on. So now what can happen is, I can have this sample coming from some other sinusoids as well. Sorry. So let's say this sample and this sample. So these samples can come from signals with different frequencies, which are basically multiples of fs, which are integer multiple of fs. The same sample can belong to either this sinusoid or this sinusoid, or other multiple sinusoids with frequencies of nfs plus minus f naught and different phases. This thing can happen. So now we are having a component here and here, and 1 second, let me admit this. Yeah, so now if I look at the original signal xt, so this is this thing here, what I have drawn is basically the frequency domain representation for sampled signal. Okay, so this is for the sampled signal, and if you look at this thing here, this thing, only this shaded thing, this is the frequency domain representation for xt, that is original signal. Now when I have sampled the signal, then I may need after processing, I need to reconstruct my original signal. Like after processing, I need to reconstruct back the original signal. So for that, what I need to do is I need to pass this through a low pass filter, that is just preserve this much frequency domain representation and make these all zeros. So now what is happening is, if my f naught is less than fs minus f naught, then there won't be, this particular component won't be available. Like, so for example, if I have a low pass filter something like this with some cutoff frequency, let's say fc, then the component which is the replicated component which is coming due to sampling will not have any effect here. That is, if this f naught is less than fs minus f naught, if this f naught is less than fs minus f naught, then there won't be any overlapping, and this condition will be no aliasing. Now suppose instead of that, the sampling frequency is small enough such that we have this f naught here, and let's say this is fs, and here somewhere I have fs minus f naught, something like that, and here I'll have fs plus f naught, something like that I have. And then in order to recover it back, I pass this through a low pass filter like this. So I'll have this particular component which is coming due to sampling but was not available in the original signal. So now I am having this particular overlap thing coming up due to sampling. And this particular case, when my f naught is greater than fs minus f naught, so here my f naught is greater than, this f naught is greater than fs minus f naught, at that point I'm getting an additional component here which is arising due to this particular sampling process, and this additional component, presence of this additional component due to sampling, is known as aliasing. Is it clear now?
Yes, ma'am.
Yeah, thank you. Any other doubts? Okay, if there are no doubts, then let's go on and solve some questions. So let's start with the first question that I have planned to cover today. So it says that how many samples are required so that we can perfectly reconstruct the signal given by yt equal to a e power bt. So the signal that is given to us is yt is equal to a into e power bt, and what all other things are given to us. Assume that it is known that the signal function is an exponential function, which means that the nature of the signal, this assumption, what does this assumption say? Nature of the signal nature of the signal is known. So in order to, if I know that it is an exponential signal, I know that it takes the form of some constant multiplied by a power bt. So what do we mean by reconstructing back the original signal? It simply means that this reconstruction means that we need to find the constants a and b. So reconstructing yt is equivalent to find or to finding equivalent to find the constants a and b. So basically there are two unknown variables. Two unknown variables are there, and two unknown variables, if I need to find out the values of them, then I need two equations. And these two equations can be obtained by looking at two samples. So let's say we look at the two samples at time t1 and t2. So let's say let's consider the samples, or rather saying samples, the signal values at time instances t1 and t2. So let y1 equal to y of t1, which will be a into e power b t1, and y2 will be y of t2, or rather y evaluated at t2 or y seen at time t2, a into e power b t2. So what we can do is we can simply take ratio. So y1 by y2 will be a e power b t1 upon a into e power b t2. This a gets cancelled. This is equal to e power b times t1 minus t2. So now I can take logarithm at both sides. So I have natural log, I'll take y1 by y2 is equal to b times t1 minus t2, which is equal to, which implies that my b is equal to 1 over t1 minus t2 into natural log of y1 by y2. So I have the value of this b. Now I can substitute this b either in this or in this equation to get the value of a. And once I know the value of a, I can get I can perfectly know what this yt is. So what the question is, how many samples are required? So only two samples are sufficient. Only two samples are sufficient to obtain or to perfectly reconstruct the signal yt. But when the nature of the signal is known. Now suppose we don't know whether this yt is an exponential function or not. Suppose this knowledge is not given and you have been told that it is some signal, you don't know any particular nature of that signal, no information is given. So will your answer remain same? So the question that I am trying to ask is, will your answer remain the same if you did not know that yt is an exponential signal or not an exponential signal?
Ma'am,
Yeah.
here the yt is given, the express, it is an exponential signal. So if any signal which is given here, that the expression should be given na. So from that expression we can conclude that this signal may be exponential or other signals like that.
Okay, but let's say you don't know anything about it, but you
Anything about?
want to, let's say you are just given, let's say you are just given some frequency range of it.
Okay.
Let's say you are given that this yt lies between the frequencies in yt lie between 0 to some fm,
Okay.
and you don't
Yes,
know
madam. In that
anything.
case,
Yes,
can we say that we will simply depend on the Nyquist criteria?
exactly, correct, exactly.
Okay,
So
ma'am. Thank you.
yeah, yeah. So the number of samples that you will require in 1 second will be equal to your sampling frequency, and you will require some fs sampling rate into the number of samples to reconstruct it back. So that everything will depend on the Nyquist criteria, how many samples you need to reconstruct it, or rather how many samples you need per second to reconstruct back the original signal. So that will be entirely depending on how you will design your sampling rate, which will depend on how the maximum frequency that is present in your signal, and then you will have to properly design your sampling frequency, and then you can answer this particular question. So it may not be the case that you are given an equation and then you will solve like a mathematical simultaneous equation kind of thing. That may not be the case every time, and you will see it soon in coming questions. So yeah, this first part of the question was basically to fool you that it is an exponential signal and then it has an infinite bandwidth. Then how will you reconstruct? Then your sampling frequency will be infinite. But no, when you're having, or rather when you know that this is of this particular form, the question boils down to simple mathematical question where you just need to find the a and b constants and nothing else. But when you don't know that it is a into e power bt kind of signal, then you can't do such kind of mathematical jugglery. You will have to take into account the Nyquist criteria and other things. Proper signal processing tools will be required. Any other questions? So I'll just write it down that if we don't know the nature of signal, the answer will depend on the frequency content and Nyquist criteria. Okay. If there are no questions, then I'll move on to the next question that I have today. Okay, so the next question says, okay, so this first question was like all the questions that I'm covering today were the part of the assignment that was posted last year for the same course. So, yeah, similar kind of questions might arise. So, in upcoming quizzes or maybe your final exam. So, that's why might be helpful. So, this question 2 says the following discrete time system effectively acts as a. So what does this system or the block diagram, we are given this block diagram of this system. So how does it act as? What does it act as? So in order to that, let us first construct, or let us first find out the input output relation, that is the relation between this output yn. So this yn is my output and this xn is input. So let us try to find the relation between this output and input. So what is happening here is, here we are having xn, here also we'll have xn, and this xn then passes through a unit delay block. So when it passes through a delay block, we'll have a delay of 1 unit, which will give us xn minus 1. And now here this xn is coming up with a plus sign, and then it gets added with minus of xn. So we'll have this xn minus 1. So what do we have is this yn, or let me write it specifically, input output relation it is yn equal to xn minus xn minus 1. So this is basically, this completely characterizes my system. This characterizes my system. This simply is an input output relation which tells me properly that if I have an input xn, what will be my output at every time instant. I don't require any other thing to define that system. So now what is asked is, how does the system behave, or how does the system effectively acts as? So if we look at carefully, at the current time instant, let's say at some nth time instant, it takes the current sample value and subtracts the previous sample value from it. It takes the current sample value and it subtracts the previous sample value from it. So what does this indicate? This acts like a differentiator. Yeah?
It's a differentiator, madam.
Yeah, exactly. Any questions?
Madam, what if any weights involved here, like some 2 into xn minus?
What? 2 into xn minus some constant, let's say 3xn minus 1.
Oh, yes, madam. Yes, madam.
Yeah, this will be a finite impulse response filter, and we'll have to check its frequency domain representation, what kind of filter it is. It might be a low pass, band pass, that kind of things. Even
Okay,
like
madam.
basically this is also some sort of filter. Every LSI system is equivalent to a filter. This is also some sort of a filter, but the nature xn minus 1, this is particularly a differentiator kind of thing. But when weights are involved, we'll have to check whether it is a low pass, band pass, or you can't directly say by looking at the expression. Yeah.
Yes, madam. Thank you, madam.
Yeah. Okay, if there are no other questions, then let me move ahead with the next question. So what is given is the, yeah, any question?
Ma'am, how this expression can represent a filter?
That we'll see in coming lectures. We have
Okay,
filter
okay,
design and everything. Yeah.
okay.
Yeah. We will have that Z transform and other things coming into picture. At that time, you will understand it better. So let's
Okay.
wait to answer that question for the coming weeks.
Okay, thank
Yeah.
you, ma'am.
Okay. So the next question says the analog signal xt is given by xt equal to 2 cos 2000 pi t plus 3 sin 6000 pi t plus 8 cos 1200 pi t is sampled at 5000 hertz. What is the discrete signal obtained after sampling? So what we are having is xt, the signal that we are given is xt equal to 2 cos 2000 pi t plus 3 sine 6000 pi t plus 8 cos 1200 pi t. And when we are sampling it, so after sampling, we have xn. And how do we define this xn? This xn is simply x of n times ts. But do we have ts? No. Instead of ts, we have this sampling frequency. So this 5000 is basically my fs, which is equal to 1 by ts. So what we have is, we can write this equivalently as x of n by fs. So this I can write as x. So therefore I can replace t in this equation with n by fs, or rather x of n upon 5000. So if I do that, what I have is 2 times cos of 2000 pi n upon 5000 plus 3 times sine 6000 pi n upon 5000 plus 8 cos 1200 pi n by 5000. So this I can simplify as cos of 2 by 5 pi n plus 3 times sine 6 by 5 pi n plus 8 times cos of 12 by 5 pi n. Simple question. Any doubts?
Ma'am, the last one will be 12 upon 50.
So no. This is 5000. My sampling fs is 5000. So this will be 5000. So 12 upon 50. Yeah. Thanks. Any question? Okay, if there is no question, I'll ask one question to you people. If I want to reconstruct back xt from this xn, this particular xn, is it possible? So what I need to do is, I have these samples xn, and this xn I have obtained by sampling this particular xt at a sampling frequency of 5000. Now I have done my processing. Now what I need to do is, I need to reconstruct back this xn to get this xt. Is it possible? Will I get this exact xt?
Yes, madam, possible, madam, because in the given signal, the maximum frequency component is 600 Hz. So if you pass the samples through a low pass filter, at a cutoff frequency of 6,600 Hz, I think we may reconstruct the signal.
I have.
And
How are you saying that the maximum frequency component present is 600 hertz?
because the third component 8 into cos 1200 by 18, madam.
See,
So there the frequency is 600 Hz.
see, this is having a frequency of 600. This is having a
Yes, madam.
frequency of 3000, and this is
Three.
having a frequency
Oh,
of
okay, okay.
1000.
Okay, madam. Sorry, madam. Okay, okay.
Yeah, yeah.
Then 3K. Yes, yes. We can use 3K filter. Yes.
Yeah, but now I'm sampling it at 5000. Is it satisfying my
A
Nyquist
bit.
criteria?
Okay, okay. Yes, madam. Yes, madam. Yes, yes. So the sampling rate must be 6,000 H,
Yeah,
but we are using at 5K.
yeah.
We may not exactly reconstruct the signal, but somehow the signal will be reconstructed, madam.
No, somehow, no, you won't get exact signal. There will be additional sinusoid which will be present because of this particular component here, which will be at
Yes,
5000
madam.
minus 3000. At 2000, it will overlap with you'll have additional frequency component here.
Okay, madam. Okay, madam.
Okay, so you can't do it. Yeah, NS Murthy Sharma has raised hand. Can you please let me know your question?
Madam, we have to strictly fulfill the Nyquist treatment, no, madam?
Yeah. It's not fulfilling the Nyquist criteria.
Yeah.
That's why we can't reconstruct.
Madam,
If
can you put the first question, madam?
this one?
First question.
Huh.
Uh, is the question, how many samples that is not answered, no, madam? Only 8 are answered.
2 samples
How 2 samples, madam?
at T1 and T2.
Only T1 and T2.
Yeah, you take any 2 time instances where T1 not equal to T2.
Because you are having two unknowns, you have to take two instances, no, madam?
Exactly.
Thank you, madam.
Yeah. Okay. Any other questions? Okay, if there are no questions, then let me move on to the next question that I have. So this is question 4th, and it says that given the following relations of signal, following signal and CTFT relations, find the value of V of j omega, which is CTFT of Vt. So what is Vt? Vt is x1t convolved with x2t convolved with x3t. So this star, or rather this asterisk operation indicates convolution. Yeah, please ask your question.
Am I audible, madam?
Yeah.
Please magnify the question, madam. I cannot able to write it.
You want to? I want like
Uh,
this.
Thank you, madam.
Yeah. Don't worry. This PDF will be shared with you. Don't worry. If you
Okay.
miss onto anything,
Okay.
this PDF with solutions will be available on.
Thank
Yeah.
you.
Yeah. But I'll increase the fonts from coming lectures. No issues. Yeah. I'll request you all to please mute yourself when you don't have questions. You can unmute freely whenever you want to ask. So what we have here is given the following signal and CTFT relation. So the CTFT is basically continuous time Fourier transform. So I'll define that first, and what we need to do is we need to find the value of CTFT of Vt, which is V of j omega, where Vt is given by this particular convolution operation. Yeah, ask your question, sir.
Madam,
Huh.
for conjugate you are using the x1 star, but the mentor used the x bar. You use it complex conjugate x star is sufficient, madam.
You can use anything. It's
Anything,
fine.
but it will be confusing, no, madam.
I have, okay, for avoiding confusion, I am starting using bar.
Standard textbooks will be using that star only, no, madam, convolution.
Yeah, but it's fine. It's fine. The star and bar can be used both. Just we need to define it properly.
For giving questions, you will be using star only, no?
In exam,
In exam or in assignment, you will be using star only, star notation only, no, for conjugate.
no, I don't think so. It will be bar most probably. Whatever the instructor uses in
Madam,
the,
the standard notation, no, why it is special for IIT Mumbai?
I don't know, sir. I don't belong there.
No, sir. No, we should use the notation which is universally accepted, no?
I request you to please write to the instructor there.
Instruction question.
Yeah. You just post it in the common
Okay,
forum which is there.
I'll email to the teaching assistant, madam.
Yeah. Please let them know that
Uh,
like this issue you are having, so they'll handle it properly.
yeah.
Yeah, these
Because
things belong to instructor. These are not in our hand.
Openham textbook also, he will be using star only, no?
Yes, sir. I understand what you are trying to say.
Openham or some other book, we have Royakis. Royakis also will use the same notation, no?
Yes, sir. I understand what you are saying.
Uh,
I
so I have to
understand
put a
that.
question only. Okay, I'll put a question, madam. Thank you.
Yeah. Please let them know. They'll handle it properly.
Okay.
Yeah. Thank you. Okay. So what we need to do is we need to find the Fourier transform of this Vt signal, which is and this Vt is x1t convolved with x2t and convolved with x3t. So let me first define this CTFT, which is continuous time Fourier transform. So the CTFT, if I am having a continuous time signal xt, then its continuous time Fourier transform x of j omega will be given by integral. This integration is over t, so t running from minus infinity to infinity xt into e power minus j omega t dt, where this omega is angular frequency. Okay, so we are given that this xit has a CTFT as capital Xi of j omega, and this I belongs to 1, 2 and 3. And what we are given is this x3t is equal to x1 conjugate of x1 of t1 minus t0 conjugate plus x2 of t1 minus t0 conjugate. And this Vt is simply convolution of this. And we need to find the Fourier transform of this quantity. So in the signals and systems course, very initial signal and systems course, we have seen various properties of this Fourier transform. So that shall be handy in order to find this particular thing here. So what we are having is this Vt is equal to x1t convolved with x2t convolved with x3t. So this V of j omega will be simply Fourier transform of x1t convolved with x2t convolved with x3t, and using the convolution in time property of this CTFT, this is simply equal to the multiplication of Fourier transform of x1 omega with Fourier transform of x2 of t into Fourier transform of x3 of t. So this V of j omega will be equal to x1 j omega into x2 j omega into x3 j omega, and this is through convolution property. Okay, so now this x3t is related to x1t and x2t. So we need to find the value of x3 of j omega in terms of x1 of j omega and x2 of j omega. So in order to do that, let us find the Fourier transform, or rather be specific, CTFT of xi of t minus t naught conjugate. Okay, so we need to find this. So this we'll do in two steps. First we'll find the Fourier transform of xi of t minus t naught, then we'll take its conjugate and find its Fourier transform. So let us consider what I'm writing. Yeah, so let us first find out the Fourier transform of xi of t minus t naught. So the Fourier transform of this quantity can be easily obtained through the time shift property of Fourier transform, which says that if I shift in time domain by a value t naught, then in frequency domain I'll get a scaling by a complex exponential e power minus j omega t naught multiplied by the Fourier transform of original signal. So this is the time shift property of CTFT. So this we have. Next what we need to do is find the Fourier transform of xi of t minus t naught conjugate. So for that what we'll do is let xt be defined as xi of t minus t naught, and we have this property that x conjugate of t has a Fourier transform of, sorry, let me be consistent, x conjugate of t has a Fourier transform x of minus j omega conjugate. So this thing is this is also the property of Fourier transform. So this is complex conjugate property. So here my x of omega is this quantity. So this quantity here is x of j omega, and this is x of t. So this xi of t minus t naught will have a Fourier transform of this form. So we need to take the conjugate as well as substitute minus j omega instead of j omega. So what we have is e power, if we take the conjugate, this e power j omega t naught will be e power minus j omega t naught will be e power j omega t naught, but now we need to replace this omega by minus omega t naught and xi of minus j omega conjugate. So this becomes e power minus j omega t naught xi minus j omega conjugate. So what do we have is xi of t minus t naught conjugate has a Fourier transform of e power minus j omega t naught xi of j omega, sorry, xi of minus j omega conjugate. And what is this x3 of t? This x3 of t is x1 of t minus t naught conjugate plus x2 of t minus t naught conjugate. So if we use this relation which we have just derived in order to get the values of, in order to get the Fourier transform, then this x3 of j omega will be, the Fourier transform of this quantity will be e power minus j omega t naught x1 of minus j omega conjugate. So this will be e power minus j omega t naught into x1 of minus j omega conjugate, plus in similar fashion the Fourier transform of this x2 of t minus t naught conjugate will be e power minus j omega t naught x2 of minus j omega conjugate. So this I can write as e power minus j omega t naught x1 of minus j omega conjugate plus x2 of minus j omega conjugate. And what we had to find out, we wanted to find out this quantity which is v of j omega, which is x1 of j omega into x2 of j omega into x3 of j omega. So what we have is v of j omega is equal to x1 of j omega into x2 of j omega into x3 of j omega. So let us substitute back the value of this x3 of j omega which we have just obtained. So now we have x1 of j omega into x2 of j omega into e power minus j omega t naught x1 of minus j omega conjugate plus x2 of minus j omega conjugate. So this is the value of v of j omega. Any questions?
Madam, in time shift property, xi of t minus t naught, its conjugate, its Fourier transform is e power minus j omega t naught. But when you take a conjugate, will I think that minus and one more minus will come, no, madam?
1 second, I'll tell. 1 second.
Oh.
Okay, so let's do it step by step here. So we need to, what we need to do is, what I'll do, I'll first substitute, I'll find out this quantity. Okay, so x of minus j omega, let's find out this first. So that will be e power minus of minus j omega t naught into xi of minus j omega, right? So this is e power,
Okay, madam. Yes, I understood, madam. Yes, madam.
yeah. And when we take the conjugate, you will get this quantity.
Yes, yes, madam. Yes, madam.
Yeah,
I
it's
missed
fine.
that.
Yeah, it's
Yes.
fine. Any other questions? Okay, if there are no questions, then let's move on to the next question. Yeah. So what we are having here is, we are given three sinusoids. x1t is a1 cos omega t plus phi 1. x2t is a2 cos omega t plus phi 2. And x3t is omega t, a3 omega t plus phi 3. So all of these sinusoids are having same frequency, but they differ in amplitude as well as in phase. Okay, so what we say is each of this xi of t each of this xi of t is sampled to obtain xi of n, where this I ranges from 1 to 3. Now, what we have is xn. We have this signal xn equal to x1n plus x2n plus x3n. Now, this signal, this sample which we have obtained, is almost perfectly reconstructed to obtain xt equal to x1t plus x2t plus x3t. And it is found that this x of t is a sinusoid and can be represented in this fashion. That is xt equal to a cos omega t plus phi. And what we are asked is we need to find the values of a and phi. These are the two things that we need to find out. Is the question clear? So what it at the end says is, if my xt is equal to x1t plus x2t plus x3t, if we have it like this, and this xt is a sinusoid which can be represented as a cos omega t plus phi, we just need to find the values of a and phi. So let us find it out. So what we have is xt is equal to x1t plus x2t plus x3t. So this I can write as x1t is a1 cos omega t plus phi 1 plus a2 cos omega t plus phi 2 plus a3 cos omega t plus phi 3. Okay, so now what we'll do is we'll use the formula cos of a plus b, which is equal to cos a cos b minus sin a sin b. This we'll use for all of these three things. So let's do that. So this is equal to a1 times cos of phi 1 into cos omega t minus sin phi 1 sin omega t plus a2 into cos phi 2 cos of omega t minus sin phi 2 into sin of omega t plus a3 into cos phi 3 cos of omega t minus sin phi 3 into sin of omega t. So now what we'll do, we'll combine this cos of omega t terms and we'll combine this sin of omega t terms. Okay. So what we have is, let's say we have this, the coefficient of this cos of omega t, let us construct that first. So we have a1 cos phi 1, this one, or let me use the color scheme properly. So what we have is a1 cos phi 1 plus a2 cos phi 2 plus a3 cos phi 3 into cos omega t minus a1 sin phi 1 plus a2 sin phi 2 plus a3 sin phi 3 into sin omega t. So this xt in a concise way we can write as summation I equal to 1 to 3 ai into cos phi I into cos of omega t minus summation I equal to 1 to 3 ai sin phi I into sine of omega t. And what we have been given is this x of t can be represented in this form. So let's say this is equation 1. So we are given that this x of t can be represented as a times cos of omega t plus phi. So again applying this cos of a plus b identity here, what we have is a times cos phi cos of omega t minus sin phi into sine of omega t, which we can write as a cos phi into cos of omega t minus a sin phi into sine of omega t. Okay, and let's say this is equation 2. So if we look at these two equations, that is this one and this one, these both of these represent the same quantity. So if we combine or if we compare these two things, then this particular quantity should be equal to this quantity because they are coefficient of this cos of omega t. Similarly, this quantity here will be coefficient of this sin omega t, that is this quantity. So what I am trying to say is this quantity here is equal to this quantity, and similarly this quantity here is equal to this quantity. So this a cos phi is equal to summation I equal to 1 to 3 ai cos phi I, and a sin phi is equal to summation I equal to 1 to 3 ai sin phi I. So now what we'll do is, let's consider a cos phi square plus a sin phi square. So this will be equal to a square into sin square phi plus cos square phi, which is equal to a square. And again this quantity, if we substitute these two values, then this will be equal to summation I equal to 1 to 3 ai cos phi I whole square plus summation I equal to 1 to 3 ai sin phi I whole square. So this is equal to a square. Therefore a is equal to square root of this quantity, cos phi I square plus summation I equal to 1 to 3 ai sin phi I square and its square root. So this is the value of a that we are having. Now in order to find the value of phi, we can use either this equation or this equation, or simply take the ratio of this equation and this equation. So what we have is sin phi upon cos phi, which is equal to tan phi is equal to summation I equal to 1 to 3 ai sin phi I upon summation I equal to 1 to 3 ai cos phi I. So this implies that phi is equal to tan inverse of summation I equal to 1 to 3 ai sin phi I summation I equal to 1 to 3 ai cos phi I. So these are the two things that we had to find out. One was A and one was phi. Any questions? Okay. If there are no questions, then let's move on to question number 6. Okay. So this question says a signal having zero spectral content for frequencies greater than f max is sampled and quantized to get 4 bit per sample at each step. What is the upper limit? What we need to find is the upper limit on f max such that the signal can be fed into a channel transmitting at a rate of 14 kilobytes per second without any loss of information. Okay, so without any loss of information, what does this mean? So first thing is we want to sample greater than 2 times fs, where fs is the sampling frequency. And what all things are given to us? First thing that is given to us is the signal is having a spectrum something like this. Something like this. That is, the spectral content after f max is 0. Okay, and what is given is, let's say that we sample let the signal be sampled at fs sampling frequency. So what does this mean? This means that in 1 second fs samples are generated. And another information that we have is it is quantized to get 4 bits per sample. So each sample is represented.
Madam, here capital B is bytes, no, madam?
Yeah, bytes.
Oh, yes, madam. Yes, madam.
Each sample is represented by 4 bits. Okay, therefore, in each second, Fs into 4, where Fs is number of samples per second, and each sample is represented by 4 bits, that is 4 into Fs bits are generated. Okay, now what does Nyquist rate say? Nyquist criteria say? So using Nyquist criteria, or yeah, before doing that, so if in each second we are having this 4 into Fs bits, so these 4 into Fs bits are to be transmitted in 1 second. So this is equal to the rate at which we are transmitting over the channel, or it is also called as the rate of transmission, which is given as 16 kilobytes per second. So this 4 Fs bits per second is equal to 16 kilobytes per second. So this I can write as 16 into 8. This will be kilobits per second into, let's say, approximately 10 raised to 3. It should be 1024. So, but for simpler calculations, let it be 10 raised to 3 bits per second. Okay, therefore this Fs is equal to 16 into 8 into 10 raised to 3 by 4, which is equal to 32 into 10 raised to 3. Okay, so let's say this is the first thing that we are having. Now what does Nyquist criteria say? So using Nyquist criteria, the Fs should be greater than 2 times the maximum frequency present in that signal. So this Fs should be greater than twice the maximum frequency, such that we won't have aliasing and there won't be any loss of information. So what is Fs? This Fs is 32 into 10 raised to 3, and this should be greater than 2 times Fmax. So this Fmax should be less than 32 into 10 raised to 3 by 2, which is 16 into 10 raised to 3, which is equal to 16 kilohertz. So if I'm having a signal with bandwidth of 16 kilohertz, I can transmit with a rate of 16 kilobytes per second. If I'm quantizing it, each sample at 4 bit, that is 16 quantization levels. Any questions?
Madam, this is the signal bit rate, right?
Which one?
How much we got? That is 32 kilohertz. Is the 32 kilobits per sample is the our signal bit rate
This
at which the
32
bits are
thing is
kept.
sampling rate. This is sampling rate.
Uh, okay, man. Then, okay, 16 kbps is the, yes, madam,
Yeah, this is the rate.
at which we are transmitting
Yes.
the signal,
Yes.
but no information given about channel bandwidth, no, madam.
No. It's fine.
Okay, okay.
This
Yes,
channel bandwidth is assumed to be larger than signal
yes, yes,
bandwidth.
madam. Yes, yes. Then only we can transmit
Yeah,
this.
then
Yes,
only
madam.
we can transmit.
Yes, madam. Yes,
Let's not get into details for communication. Let's stick to signals and systems.
madam. Okay, madam.
Yeah. You're right that we need a channel bandwidth higher than this. Assume entire bandwidth is available for communication for now. For now. Okay. Any other questions? Okay, if there are no questions, then let's move on. So it's a simple question. It was just simple thing asked in last assignment, that aliasing is a signal in signal processing is caused under which conditions. So let's ask you all, what is the condition when aliasing is caused? When does aliasing occur? This we have discussed multiple times before this particular question.
When f0 is greater than fs minus f0.
When f0 is greater than fs minus f0. Correct. What is f0?
F0 is the signal frequency.
Okay, but that is for sinusoid. Now can you generalize it for any signal? You're correct. Can you generalize it
Fs
for
must
any
be
signal?
greater than 2 times of Fm.
Fs must be
For the aliasing, here Fs must be greater than 2 times of Fm.
for aliasing, Fs must be greater than 2 times of
No,
Fm.
sorry, less than 2 times of Fm.
Correct. Correct. So aliasing occurs when my sampling frequency is greater than 2 times Fm. Yeah, please ask your question, sir.
Is it completely evil, or it can be useful somewhere? This aliasing condition.
It can be useful somewhere, but I can't recollect the applications.
Because sir told that it may not be evil like that.
Yeah, it might be useful in some situations, but I don't remember any applications. I can get back to you in the next lecture, or probably.
It necessarily not be an evil. Am I right?
Yeah. Okay. However, when we are going for signal processing applications and applications for communication, where the signal is important to us, where the signal carries some information, in that situation, this aliasing is evil. We don't want aliasing in that situations. Okay. So next thing is, which wave has infinite number of continuous derivatives? This is also a simple question. Just to get away with too much math, I put it between these questions. So what's your answer? Yeah, sir.
It is sine or exponential, madam.
Correct. So let's go with sinusoidal, or which exponential, sir?
Simple, madam. E to the power of x.
Okay. Okay. Any questions on this? I won't think will be, but still, if you have any questions, just let me know. Otherwise, we'll go to the next question. Okay, so this question says, which of the following continuous time systems are qualified enough to behave as an ideal low pass filter with cutoff frequency equal to omega c, and this omega c is angular frequency. Okay, and we have been given 4 options. So out of these 4 we need to look at which is the correct option. Okay, so for that let us look at how this low pass filter looks. So let's say this h of j omega be the frequency domain or Fourier transform or continuous time Fourier transform of the filter, which is given by ht. So its frequency domain representation will be like this. This is omega axis, this is cutoff frequency omega c, this will be minus omega c. So this is the frequency domain representation. For the low pass filter. So this is low pass filter. And why is it called low pass? Because it allows or it passes all the lower frequencies and attenuate all the high frequencies. And why is it an ideal low pass filter? Because we are having a sharp cutoff here, like sharp thing here. Like for this, anything before this particular point is 1. So this is having amplitude 1, no attenuation, and suddenly we'll have 0. That's why this sudden change is required, is ideally needed, which may not be possible. We'll see that in filter designing thing that it's difficult to achieve this particular kind of structure. But yeah, if we are having this low pass filter, so what we need to find is how to represent this in time domain. So what we need to do is we need to find h of t. So this thing we need to find out, and all of these things here are basically ht, and his filters are LSI or LTI systems, and that's why we can represent it through convolution, like input output relation can be given through convolution operation simply. So that's why we are having it in this form. So the question is simply we need to find the inverse CTFT of this signal, this Fourier transform here. So if I am having h of j omega, then how to get h of t from it? So this h of t is equal to 1 upon 2 pi integral, this integration will be over omega, minus infinity to infinity h of j omega into e power j omega t d omega. Now here this omega is non-zero only in this duration, that is minus omega c to omega c. So this I can write as 1 over 2 pi integral from minus omega c to omega c, and in this duration this h of j omega is equal to 1, so it is 1 into e power j omega t d omega. So this comes out as 1 upon 2 pi e power j omega t upon jt evaluated over the range of minus omega c to omega c. And this is equal to 1 upon 2 pi jt e power j omega c t minus e power minus j omega c t. So if we look at the options here, so this thing e power j omega c t minus e power minus j omega c t upon 2 pi jt is the answer. So this particular thing option is the answer. Any questions?
Ma'am,
Yeah.
Ma'am, can we recognize any filter from any equations like in that way?
Means?
Yeah, so you are considering here a low pass filter.
Yes.
From this equation, which one is represent a low pass filter? If we are considering a high pass filter, can we represent? Can we find from the equation that this equation will represent a high pass filter?
For ideal high pass filter, you can try this out. How will an ideal high pass filter look? So it will be 0 till some cutoff
No.
frequency,
After that,
and after
yes.
that it will be 1.
Yes.
Right? So now what?
Yes.
Now you can try to find the inverse Fourier transform of this quantity.
Yes.
So if you mathematically know exactly how your frequency domain representation is, then in order to get the time domain representation, just take the inverse Fourier transform. You will get the equation. Okay.
Okay. Okay.
Yeah. So if you know how which frequencies you want to attenuate and which frequencies you want to uh, amplify, and amplify by what factor, all these things you know, then you can try getting the equation. And we'll see all of these things in greater detail when we do filter designing. But
Yes,
before,
ma'am.
yeah, yeah. So before that, let's just play with this signal here a little bit. So this is e power j omega ct minus e power minus j omega ct. I can write it as upon 2j into 1 upon pi t, and this is equal to this quantity here is simply sine of omega ct upon pi t, and this thing is a sinc function. And yeah, you can look at this, like you can remember this Fourier transform pair, sinc and rectangle, and these are like sinc will have a Fourier transform of rectangular pulse, and rectangular pulse will have a Fourier transform of sinc. So these things you can keep in mind if you are going for any competitive exams, or yeah, it is handy if you know these things. So just I wanted to emphasize on this little bit. It's not that difficult, but still I wanted to emphasize it. Any other questions? Okay, if there are no questions, then let us go ahead. So yeah, I purposely added next two questions just to show that the questions may appear too big, but those are really simple one. Unnecessarily too many things are added in it. It's a simple one. And yeah, here I forgot to insert options. So the first option was fs equal. I just add it and then we'll go ahead with the question. Yeah. Okay. So let's read this question. Suppose our task is to sample a purely sinusoidal signal xt equal to a sine 2 pi f naught t. So this is the signal that we are having. This is xt equal to a sine 2 pi f naught t, and the sampling frequency fs is such that the sampling duration is ts equal to 1 by fs. We knew that from the same sampled signal, multiple sinusoidal reconstructions are possible. For example, let me write it as xk of t. On for example, this thing, oh sorry, on sampling this xt signal, this gives rise to these signals, that is x1t, xn equal to a sine 2 pi f naught plus minus k fs into nts, which is equal to this quantity, which is equal to this quantity. This is the same as what we would get from sampling xt. So if we sample this signal xt, or we sample this signal x1t, so what is special about this x1t is this x1t has a frequency of f0 plus minus kfs, and if we sample this, one component of it will be available at this component, and similarly, like the sampled version of this and this will be exactly the same, the spectrum of it will be exactly the same, because it results in the same signal. There are infinitely many such sinusoids possible that can be sampled to get the same discrete time signal. Now suppose we try to reconstruct the original signal by taking the sum of all such possible sinusoids and passing it through a suitable ideal low pass filter. So what we need to do is, we sampled a signal xt, or let's say x1t, and I got some samples. Now what I want to do is, I want to reconstruct back the original signal. I want to reconstruct back the original signal, and I should get xt if I sampled xt, and I should get x1t if I sampled x1t. So suppose we try to reconstruct the original signal by taking the sum of all such possible sinusoids and passing through a suitable ideal low pass filter to get a single sinusoid, the single sinusoid which we sampled. For which of these sampling frequencies we would correctly get back the original xt? Assume the sampling is done at t equal to nts. So these are your 4 options. What will be your answer?
Ma'am, option C.
Okay, and why?
Ma'am, this Nyquist criteria is followed.
Okay, what is the Nyquist criteria?
Fs should be greater than or equal to 2 times of Fm.
Greater than or equal to or greater than?
Ma'am, for retracing the original signal, it should be greater than. Option D, sorry.
Yeah, 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 correct. Correct. Option D. So what does the Nyquist criteria say? So we have sampled xt. We want to sample xt to get xn, and we need to reconstruct back it to get xt. So if that is the case, we want our fs should be greater than 2 times f0, and the option that satisfies that is option D. Now suppose we want to now suppose we want to sample this xt, and let's say this xt is simply plus, this x1t is simply a sine 2 pi f0 plus k time fs. So the sampling frequency for this should be greater than 2 times f0 plus kfs, and it can't be sampled at fs. Similarly, if it is simply a minus, then this signal has to be sampled at Nyquist rate of Nyquist of sampling rate greater than 2 times f0 minus kfs, but it can't be sampled at fs. Other, if we sample it at fs and then uh, pass it through a low pass filter, we'll get this. Or if we sample it with a low pass filter of having cutoff frequency greater than this particular frequency, we'll have multiple frequency components present there, which will be a sum of sinusoids, and it will not be the original signal that we wanted. I hope this is clear. If you have any doubts, please let me know.
Madam, a small doubt here, madam.
Yes.
Is x1 of t is the reconstructed version from x of t, or suppose x of t is sample, after sampling, if we reconstruct, then x1 of t is possible, like that, madam?
See, x1t, we sampled x1t.
No, madam. What I'm asking, x of t is there.
Yes.
From x of t, x1 of t is reconstructed, or what?
No, no, no,
X
no,
of
no, no,
t
no.
is sampled, then x1 of t is
No, no,
reconstructed.
no, no, no.
Oh,
The
oh,
question
okay,
is, we want to sample xt.
okay.
We want to sample xt and then we'll get x of n. And that x of n
Yes,
is equivalent to these three things.
yes.
Right. Now consider another signal, which is
Okay, okay.
x1t.
Okay, madam.
If
Okay,
we
madam.
sample x1t, we'll get
Okay,
again this signal. If we sample
okay,
x1t with same sampling frequency as fs, we'll get
okay,
this signal.
okay.
So if we reconstruct back and pass through a low pass filter, there is an ambiguity whether it is xt or it is x1t. So if we don't want that ambiguity, what should be the sampling frequency?
Madam, can you pictorially represent like blocks?
Okay. Okay. So my original sinusoid was this one, a sine 2 pi f naught t. So let's say this is 0, this is frequency axis. So this is f naught. So this is the original thing. Okay.
Yes, madam.
So let's consider, instead of plus minus, let us just consider plus here, for example. Okay. Is it okay?
Yes, yes,
Same
madam.
thing will hold for minus also.
Okay, okay.
So this is xt, and let's say this is x1t. This is 0, and let's say this is fs. This is fs. So this will be present at fs plus f naught, or let's say, and let's say this k is 1. Okay, for now let the k equal to 1.
Yes, madam.
Okay, so now if I sample xt,
Yes, madam.
so if I sample xt, this component will be present, but I'll have a component here.
Yes, other components also.
Yeah,
Yes, madam.
similarly at 2fs I'll have. Also I'll have it f minus f naught, and also I'll have it at minus fs and minus 2fs everywhere. Am I right?
Yes, madam. Yes, madam.
Okay, from minus infinity to infinity I'll have replicas. Now again, if I sample this x1 of t, if I sample this x1 of t at fs sampling rate, now this
Like
original will
earlier.
be
Yes.
present. Then I'll have one replica here.
Yes.
I'll have one replica here. I'll have a replica here also. So now this thing
Yes, madam.
and this
Yes,
thing
madam.
is exactly same.
Yes, yes.
So now there will be an ambiguity. So in
Yes,
order
madam.
to remove that ambiguity, we should wisely choose the sampling rate.
Okay.
Is
Yes,
it
madam.
clear now?
Yes, madam. Yes, madam. Thank you. Thank you.
Yeah. Any other questions? Okay, if there are no questions, then let us go ahead with the last question that I had planned to cover today. So this is also the assignment question. So okay, so what does it say? One of the most common ways of obtaining the sampled version of an analog signal is to perform uniform sampling of signal by multiplying it with a train of impulses, each shifted by from the previous by Ts, that is the sampling period. This is called as the impulse train sampling. This is the same thing that we have been doing since the first lecture. That sampling is known as impulse train sampling. So this is called impulse train sampling, and we perform the same for two cases in this problem. Same normal sampling process we are doing, whatever we have been doing till now, nothing else. It is known as impulse train sampling. So all of this first few lines just say that we are sampling it at a rate of 1 by ts or with a sampling duration of ts, nothing else. Let xt be the given analog signal such that x of j omega is this and is this. Okay, so x of j omega is the continuous time Fourier transform of xt. So let us draw it. Okay, so let's see, this is omega axis, this is 0, this is, let's say, x of j omega, this is omega m, this is minus omega m. Then from minus omega m to 0, it is omega by omega m plus 1. So at omega equal to minus omega, this will be minus omega m upon omega m, that is minus 1. So minus 1 plus 1, 0. So at omega equal to minus omega m, it will be 0. And at omega equal to 0, this will be 1. Similarly, for omega equal to omega in the range of 0 to omega m, in this range, this will take the value as minus omega by omega m plus 1. So if omega equal to omega m, then this quantity will reduce to 0. When omega equal to 0, it is equal to 0. So this thing will be like this. Okay, so this is my x of j omega. Yeah, this thing is given to us, and pt is this quantity. Pt is train of impulse. So how does this train of impulse look? This is time axis. So I'll have an impulse at t equal to 0, then I'll have an impulse at ts, at 2ts, and so on. Similarly, I'll have it at minus ts, minus 2ts, and so on. So this is my p of t, and this xp of t is xt into pt. Okay, and what we have is this 2 pi by ts. This 2 pi by ts is simply omega s is greater than omega m in all the situation. Now we have been given, we perform the impulse train sampling for two cases. So the case one is when ts is less than pi by omega, and second case is ts is greater than pi by omega. So what is given is this xp of t is xt into pt. Sorry, x3 into pt, and its Fourier transform is xp of j omega. So they have given three area definitions, that is if the area under this xp of j omega between minus omega m and omega m is a omega m and 2 pi by ts, so this is simply omega s. So this quantity is omega s minus omega m, and this quantity is simply omega s. So from omega m to omega s minus omega m is A1, and 0 to omega s is A2. So now what we need to do is we need to find the relation between the areas A1, A2 and A1 and A2. Okay, so let us simplify this question. We have this signal with Fourier transform as this. This signal we have. This signal we need to sample. So let's start with case 1. So case 1 says Ts is greater than pi by omega. So Ts is less than pi by omega m. Okay. So this I can write as omega m is less than pi by Ts, or 2 I can do it like this, which means that 2 times omega m is less than omega s, which is omega s is greater than 2 times omega m. So if this is the case, if my omega s is greater than 2 times omega m, this is the condition for case 1. So now let us try to construct. Let's try to construct xp of omega. So this xp of omega is simply sampled version of it, the same thing that we are doing. So this is 0, this is omega m, this is minus omega m. Let's say this is omega s minus omega s. So what it says is omega s is greater than 2 times of omega m. And when we are doing this uniform sampling, or rather impulse train sampling, which we have been doing it every time, we saw that the replica of the Fourier transform of the original signal is available at every integer multiple of sampling frequency. So if my omega s is greater than 2 times omega m, then omega s minus omega m is greater than omega m. So this is omega s minus omega m, and this is omega s plus omega m. Then I'll have a replica like this, and again I'll have a replica like this. Okay, now what all areas are given to us? So the area from minus omega m to omega m, this one, this area is A. Then the area from omega m to omega s minus omega m, this one, this area is A1, and this area from 0 to omega s is A. Okay, so this A will be equal to this area plus this area plus this area. So due to symmetry, this area is A by 2 and this area is also A by 2. So this A will be equal to A1 plus A by 2. So sorry, this is A2. This A2 is equal to A1 plus A by 2 plus A by 2, which is equal to A1 plus A. So this is the relation for case 1. Now what happens in case 2? In case 2, we have Ts greater than pi by omega m. So Ts is greater than pi by omega m, which implies that omega m is greater than pi by ts, which implies that 2 times omega m is greater than 2 pi by ts, which implies that 2 omega m is greater than omega s, that is omega s is less than 2 times omega m, or omega s minus omega m is less than omega m. So this is the condition that we are given here. So again, let us draw the Fourier transform of xp of t. So the original one is like this. So this is omega m, this is minus omega m, and what we are given is this omega s minus omega m is less than, so let's say it is here. So this is omega s and this is omega s plus omega m. So it will be something like this, and it will be repeated in both the directions. So now again, this area from minus omega m to omega m, this one is A. Then the area from omega s minus omega m to omega s minus omega m, that is this area, is A1, and this area is simply A2. So now we need to relate this A2. So this A2 I can write as this part plus this part. So this part here by symmetry is A by 2, and this part here by symmetry is A by 2 minus A2. Sorry, A1. So therefore A2 is equal to A by 2 plus A by 2 minus A1, which is equal to A minus A1. Any questions?
Clear, madam. Thank you, madam.
If you have any questions, please feel free to ask in any part of today's tutorial. These were all the questions that I had planned to cover today. If you have any suggestions for upcoming tutorials, please let me know. The recording of this today's session will be uploaded on my YouTube channel, and the link will be available to you on the course webpage. Also, these notes will also be uploaded. These will also be shared to you all on your course webpage. If you have any queries, you can ask now or in the next week tutorial, or you can post the queries in the doubt section which is there on your course webpage.
Ma'am, the recording is how will we get the recording?
Yeah, it will be uploaded on my YouTube channel. You can search my YouTube channel with name Shivani Dhok. You will find it.
Okay.
Or the
Okay.
links will be there on the website also. It will be there.
Okay. Thank
Yeah.
you. Okay.
Madam, one question is there,
Yes.
not related with the content, but
Okay.
I want to know which environment that you have used for presentation.
The presentation I have created, like this PDF which I have created is through LaTeX Beamer format, and I'm
Yes, yes,
using
yes.
GoodNotes on iPad
Uh, Good
for
notes
for
on iPad
yeah.
for presentation.
Yes, for presentation.
Okay, madam, it is open source or
No, it's not open source.
okay, okay. Thank you, thank you.
Yeah.
Ma'am, and the last question.
Yes.
Ma'am, that area A1 is coming twice in A by 2 and A by 2.
No, no, no. See, this part, this part is A by 2, right? Only
Yes,
this
ma'am.
part. Then how can you write this part? This will be this area minus this area. So this area by symmetry is A by 2 and this
Okay,
area
ma'am,
is
yes.
A1. So that's why this area is A by 2 minus A1.
Yes, ma'am, yes. Thank you, ma'am.
Yeah. Any other questions?
Ma'am, in the very first page, you actually drew a kind of block diagram
Which
on the
page?
starting page. In the first or second page, I guess. I don't know
Madam,
when you start.
madam,
Uh, Before solving. Yes, ma'am, this one, this one.
Okay.
madam,
So,
week 2 you will be discussing next Friday, no, madam?
Sorry, can you please wait? Let her ask. Let us please let her please ask the question. I'll come to you, sir.
Okay, okay.
Yeah, yeah. Don't worry, I'll come to you. Yeah, please ask your question. Mhm.
okay, ma'am, what
About
is that? Ma'am, whenever the x of n becomes the input, the result is y of n, and the y of n is a discrete signal.
Yes, yes.
So the x of n should not be discrete, right? It should be the continuous signal, I guess.
I am not showing that it is a sampling system.
Okay.
This is representation of a discrete system where input
Uh-huh.
is a discrete signal, output is a discrete signal. If that is the case, then the system is known as a discrete system.
Okay, so
This
the
is not.
discrete system converts from the discrete one signal to another discrete signal, right?
Yes, yes, correct.
Okay, okay, ma'am. Okay, ma'am. Thank you. And
Yeah.
ma'am, if whenever the fs is equals to two times of fm,
Hmm.
so in that case, the reconstruction will be possible or not?
It may not be possible because, like, if you have the sinusoids now, so
Mm-hmm.
if you're like, if you, so what will happen is if your fs is equal to fs minus f naught, your two
Mm-hmm.
signals will overlap and they'll create constructive interference. That so if you have a cutoff frequency greater than f naught now, then in that
Okay.
situation other signals will be present there.
Okay, okay, okay. When we consider the triangular signal, at that point, there is no like the overlapping is not a very big problem. But when we
Yes.
consider sinusoidal, it becomes a great problem.
Yes, and another thing is when we are that is perfectly reconstructable if we are having an
Mhm.
ideal filter. But in
Ha,
general,
ha.
we can't have an ideal filter.
Practically, we can't have ideal
Yeah,
filter. Okay, ma'am.
exactly.
Okay, I got it. Thank you,
Yeah.
ma'am. Thank you.
Yes, sir, please ask your query. NS Murthy Sharma, sir, please
yes.
ask your query.
Uh, I think you are discussing about week 2 in next week, no, madam?
What about?
Next week 2 in
Yes,
next
yes, yes.
next Friday, no? Because the 7th is last day of submission of two assignments.
See, this was week 1, so I'll
Hmm.
discuss week 1 content. So,
So week
week
1,
2
okay.
content will be discussed before the deadline of your assignment. Don't
Oh,
worry.
okay, okay. Thank
Yeah.
you.
Ma'am, I have a small request for my side, ma'am.
Yes.
Ma'am, can you possible to change not for Friday class or
Any after 1 day we can change, ma'am? Why
It's
means I have 2 sections in this day only, ma'am.
it's very difficult
Can you
because I am also a student and I have my own commitments. So this was the most convenient slot. Actually, these videos will be available and you may write me anytime. You can mail me your queries or you can post
Okay,
in
ma'am.
that discussion forum. I'll answer. No issue.
Okay.
Yeah, don't
Okay,
worry.
ma'am.
Um, Someone is trying to
Ma'am,
speak,
can
but
you send? Ma'am, can you know your mail?
not here probably. This will go on YouTube, so I would refrain.
Okay, ma'am.
Maybe you can try searching my name, you will find it. You just post it on course discussion forum. I'll answer. Don't worry. I'll be there. The discussion forum is for that purpose only. Okay. If you have no further questions, feel free to leave the meeting. Thank you for attending today's session.
Thank you.
Yes, madam. Thank you, madam. Thank you.
Thank you for attending today's session.